say a few words about the Energy Application Society. Unfortunately, due to some conflict with my teaching schedule, I could not join the opening ceremony yesterday. Well, I want to say something about IES. Well, Industry Application Society main vision and mission are shown on that slide. Industry Application Society envisioned to be a world leader for the advancement of science and technology by linking theory and practice in the application of electrical and electronic system for the benefit of humanity. Then you can see the mission statement. I will not detail it. Just I want to remember that our byline, IES byline, is linking research to practice. And I think that we are doing today is exactly that. The attributes of Industry Application Society. IES was formed in 1965, just 1 year after my born, and 2 years after the creation of IEEE. But many of our committees are very older, because some of them, and especially the industrial application, industrial lighting, and display, has been created in 1910. Of course, not with that title, but it was existing there. Today, we are the 5th IEEE society in membership size, with more than 50,000 members worldwide. We have more than 440 chapters. Many of our chapters and many of our activities, like that one today, they are joined with other societies, our sister societies, power electronics, power energy and systems, industrial electronics, and so on. We have many student chapters in more than 30 countries, and we are sponsoring many conferences per year, usually more than 50 per year. We are also sponsoring many IEEE standards. Further, IES is a core member of other operating units inside IEEE, like transportation electrification community. We support the smart grid community and the smart cities, as well as the system council, and we are a core member of IEEE's smart village, has huge humanitarian activities. Okay, now I finish with IEEE activities and IES activities especially, and I will pass to my own presentation. And as the chairman said, and he read also my abstract, I will speak about the revolutions and the evolutions in the domain of lighting systems, and especially I want to highlight that we call today this human-centric lighting era. Why speaking about lighting? As I said in my abstract, but here I will draw your attention visually that just look around you and try to tell me how many artificial light sources and lighting systems are around you. You will see that there are many small lamps, or big lamps, or lamps illuminating your table, your computer, but also lamp used for backlight, your computer screen, your telephone screen. Globally, each of us is surrounded by more than 100 small lamps or standard lamps. Why? Because lighting has multiple usage. If you take, for example, a city, here is a photo of Toulouse by night, my university city. And you can see that light sources will be used to light monuments, also to light up streets, and there the objective is to take care of traffic security, human being security, and also has some mood that attract people in the city. Then if you look what happened inside our buildings, we need light sources everywhere for different applications. You add to that, we need light sources to make signage or display information, look any car, any train, any aircraft or boat, and try to see how many lamps they are inside. And finally, light sources, artificial light sources, they are used also to some industrial applications, nothing to do with lighting, but here we can use lamps in order to clean surface, destroy microorganisms from water or from air, make dermatological treatment against some diseases, even also making some cancer treatment by using photoactivate medicines. You see, artificial light sources, they are everywhere. And if they are everywhere, they have a huge impact in our environment, in our world globally. In fact, today, 16.5% of world electricity production, which is the equivalent of 2,900 terawatt hours, is consumed just to generate artificial light. And if you translate that in primary resources, that means coal, oil, gas, radioactivity, or renewables, we dedicate something like 2% or even higher of our primary energy resources every year to light up our world. Of course, if we produce electricity, if you take an average energy mix for our world, for all the Earth, you will find that every year we release in our atmosphere something like 1 billion and something metric tons of greenhouse gas that contributes to a greenhouse effect and the climate warming. This quantity is something like about 5% of the world annual emission, and it corresponds roughly to the total emission from 230 million people. This is the impact in the environment. Now, if you look other impacts in our economy, for example, you will see that in our world every day, we have something like 30 billion electric lamps operate every day to light up our worlds. Half of that today, they are LED-based, but we have still some progress to do there. And if you look how much money brings to lighting industry, the use of light sources and artificial lighting, you will find that we have something like $100 billion annual turnover of the lighting industry, and this turnover is growing, as you can see in the graphics, is growing constantly since at least 30 years. I think now you can understand why lighting is important, because it has a large impact on energy, environment, but also has a very large impact in our own everyday life, in our economy, in also, as I will show you later, has huge impacts in our health, in our mood also. There is the situation today. If I look the 290 or 9040 terawatt hours electricity consumed per year, you will see this huge quantity of energy is going mainly to light up our tertiary buildings. That means hospitals, schools, offices, commercial buildings. 1/3 of that, 28%, is used to light up our homes, and 8% to light up our cities. Okay, in this slide, sorry, I forgot to correct, the figure is no more 15%, but 16.5% of world electricity in average. Now, if you look country by country, you will see that Western economies, say developed economic countries, they use something between 7% of their electricity every year, up to 15% of their electricity to light up the country. with a single exception, United States. United States use something like between 19% of their electricity annual consumption and 20% of that quantity, which is a huge quantity of electricity, corresponding simply to the full electrical production of France and Italy together. Why United States are using so large quantity of light? There are several reasons. One reason is in United States, the surface to light up per capita, per person using the surface, they are much larger. Second point is that even if in the United States, some states, they took drastic resolutions in order to reduce energy inefficient light sources, and they ban incandescent lamp. Some other states, they are still continue using incandescent lamps. That means US, they are well behind other countries concerning the reduction of environmental impact of lighting. And also, third point, the last but not the least, just try to imagine Las Vegas or some other cities in the United States that they have lights everywhere, and you can understand where is going this huge quantity of energy. Now, something's also very, very interesting to know is if you go to developing economies, then you will find that the proportion of electricity used for lighting in those countries is huge. Look, 34% in Tunisia. We can go up to 40% in Madagascar. We can go up to 86% in Tanzania. Of course, even if the quantity of electricity used in those countries is still low compared to US electricity or European electricity or other developed countries, you can understand that harnessing lighting consumption for developing countries is really a target of sustainable and regional development. And you should never forget that. This is something very important. Now, I told you that lighting is responsible for more than 1 billion metric tons of CO2 every year, but that you have to know is a large part of artificial lighting is produced by discharge lamps, and discharge lamps, for some physical reasons, they contain always mercury, and mercury is a very toxic material. And today, in many countries, we ask people to recycle discharge lamps, recycle general lamps. And if I take just an example, in France, we collect every week 80 tons of mercury contaminated wastes that we need to treat and clean up, take back the mercury, and then make this type of wastes not harmful for our environment. Finally, also, when we light up our cities, our buildings, we have stray light going out and lighting also the trees, the birds, the insects, and all the animals. And in our world, we have two kinds of animals. We have animals attracted by light and animals repulsed by light. And if we add artificial lighting to our environment, we impact indirectly our ecosystem. And this can be very harmful for the next, for our future. You see many impacts of lighting. What will be the future? What will happen in 2030? Well, I am a scientist, and as a scientist, I don't like to make predictions because it's very difficult to make predictions unless if you have a crystal ball, and this crystal ball is not always very sure. But Also, as scientist, I learn and I know that if I'm speaking about large numbers, then I have a good tool that may help me to make some reliable predictions. And when I look lighting, I'm speaking about billion of people using electric lighting, billion of lamps, terawatt hours of energy, billion of US dollars for the economy, and what you want, everything is in billions. That means we are clearly in the domain of large numbers. Let's then use the average values in order to make some predictions. In 2015, we had 7.3 billion people living in our planets. I choose 2015 because I have a coherent database with all the necessary figures at that moment. And this is my starting point. At the same year, 1 billion people, they don't have connection to electrical grid. That means they cannot use electricity for lighting. Of course, they use kerosene, which is also another problem. Now, if I divide 6.3 billion people that use 2,940 terawatt hours per year, I will find that an average person living in our planet, this person is not French, is not Indian, is not American, is not Tanzanian, is not white, is not black, is just someone who is not green, if you want, and he is representative, an average situation, not always the real situation for each one of us. This average person will use something like 465 kilowatt hours per person and per year in order to create artificial light, which is not a huge quantity of energy by itself. On the other hand, in 2015, the average gross domestic product that represent how rich is a country or someone, in average again, was $10,200 per person. Why I'm speaking about GDP? What is the interest? Because some years ago, US National Lab made a very interesting study. They collected data for energy consumption for lighting, megawatt hours per person and per year, and they correlate that with the gross domestic product per $1,000 and per year. And as you can see, beyond the fact that there is a large spread of the experimental points, you can see the blue line. The blue line is the linear regression of the different red dots. And if you take the value of 465 kilowatt hours and $10,200 for 2015, you will find the green star. The green star is very close to the blue line, and this blue line represents somehow the average and the average evolution across the time. Well, okay, this is fine. What will happen next? Oh, sorry, I forgot to say that when you look the blue curve, the blue curve teaches you something very straightforward. It teaches us that as richer we are, as more light we demand, and this is something linked to our, how to say, human character. It's very difficult to go against that. Let's now use all those figures in order to make some predictions. Take 2030, and if you apply the annual growth rate of the human population, which is 1.14%, and let's cross the figures beyond COVID effects. This growth rate is almost constant since several years, and apply that to 7.3 billion people, you will find that in 2030 will be something like 8.8 or maybe more close to 9 billion people in our planet. Of course, electrification also is advancing, and we can expect that in 2030, 800 million people, they will still not have access to electrical grid. Okay? That means in 2030, we have 8 billion people that they will use electricity to produce light. And beyond economic crisis, which is an effect that has limited duration, even if this duration may be 10 or 15 years, usually the GDP, the gross domestic product, increases. This is the effect of our capitalistic system, increased by 3.6% per year. That means the average human guy or girl, I don't care, becomes richer every year. Okay, this is not always true for all people, but globally it is true. That means what? If we are richer, we will use more light, and this will go to be an additive effect to the fact that we are more people using electric light. Let's make the projection. If we take the 3.6% increase of the GDP every year, in 2030, we'll find the brown point here will give us that at that moment, we will use, if no action, if we go with a model business as usual, we'll find that each of us will use 750 kilowatt hours per year to light up around here, and that for 8 billion people. Now, if I multiply back those two figures, I will find that roughly, if I don't do any action, in 2030, I will need 6,000 terawatt hours of electricity to light up our planets, or something like 2 times more than today. Just think about, and you will understand very well that is not possible. That means we need to develop strategies in order to limit or to reduce our consumption for lighting, but not limit the quantity of light that we need. One way to do that is to use more efficient technologies. Let's look a little bit what happened in the domain of electric light sources, and or in general artificial light sources, and we can find that lighting technology co-evolutes with our species, using incandescent torches, lamps, oil lamps, candles, and things like that, is known since several 10,000 years and even more. Arriving at the end of 19th century, Edison put in the market the first electric incandescent lamp. That means still our species for several years continue to use incandescence, which is a very inefficient phenomenon to produce light in order to light up the world. From the beginning of 20th century, humans started to use an existing phenomenon, but they harness this phenomenon, which is luminescence. They create discharge lamps, and discharge lamps, they are much more efficient than incandescent lamps. And at the end of 20th century, you see almost 100 years after, we had a revolution in that domain. We discovered the blue light emitting diode, and this blue light emitting diode opened the way to us to produce white light to a very efficient way in order to light up our homes, our buildings, our cities. This was a huge step forward because the efficacy of white LEDs today is almost a double of the efficacy of any legacy light source that we can imagine. This is the situation today. What will be next? But next, most probably, will be the connected lighting. And this is that I wanted to explain you now. What will happen if we use modern technologies? In this figure here, you have some projections doing by a specialist of energy consumption in United Nations or in the International Energy Agency. You see here three curves: the green one, the red, and the blue. The green one you see from 2014 till 2020 is the consumption of electricity worldwide for lighting, and you see that we have a slight decrease, which is a very positive point. And this slight decrease is really linked to the fact that we introduce in our markets more and more LEDs. We just rely on a more efficient technology. Okay? 2020 is this year, and from that point we start to make some projections, and we have different possibilities. If we don't do anything, if we go without any new policy that push our countries, our governments to fully adopt LEDs, then you will see that you obtain the blue line, and the blue line shows that from the next years, the energy consumption will stabilize and maybe they will decrease slightly. Now, the problem here is if we push people to use LEDs, we don't impose anything here about the quality and the efficacy of those LEDs. And unfortunately, today we can find excellent LEDs with twice the efficacy of classic lamps, but we can find some LEDs with efficacy lower than the incandescent lamp. That means we needed to impose some MEPS. MEPS is the minimum efficacy performance standards. If we impose those MEPS, then you can see our productions are much better, is the red line. And finally, if we go well beyond the actual technology, then we can have that we call the best available technology scenario, and in that case, we can won much more energy. Rabindra, how many time it left? Because I forgot my watch.
Another 15 minutes.
Okay, thank you. Just tell me 5 minutes before, because I don't have my watch and I don't see the time on my computer. Okay.
Okay.
Thank you. Okay. But this is not enough. Just using the best technology is not enough. What is the way forward in order to achieve more lighting? Okay, thank you. What is the way forward in order to make more substantial economies, but not only? Don't forget that when we switch on or off the light, of course we consume energy, but we do it because we need that light, and we need a given quality of the light. Let's look what happened in the history of the electrical lighting and what will happen in the future. If we start at the beginning of 20th century, when affordable electrical lighting arrives to our lives, the only problem that we had to solve at that moment was to light up. Being able to push a button and get light, switch back the button and cut the light was magic. If you go only with that mentality, the only thing that you can do is just to enhance the technology. In parallel, if you go around 1930s, the first technology for sensors has been developed. That means we start to develop sensors able to say if someone is present in a place, sensors to measure the temperature, sensors to measure the available light quality. But this has been completely independently. And then we arrive at around 1917 with the first oil crisis, and our governments, our politicians discover that lighting uses huge quantity of electricity. We need to do something in order to reduce this consumption. And then we discover the political word, is not a scientific discovery, called energy efficient lighting. How we can do energy efficient lighting? An idea is just connecting sensors with existing lighting technology, and instead to switch on and off the light by yourself, the system can do it by you. Okay, this is a good point. And of course, we continue enhance our technologies in order to get more efficient light sources. But even from 70s till end of 90s, we completely forgot that human being needs a given quality and quantity of light in order to perform its task. That means we completely forgot that we call today the human factors. And with the arrival of LEDs, the possibility to have light sources with huge variability in the quality and the quantity of light opened the way to connect human factors to energy efficient lighting. And industry today creates a new political world, which is the human-centric lighting. What means human-centric lighting? It's just energy efficient light that responds as best as possible to our needs for light quality and light quantity. In parallel, if you take into account all the developments in information and communication technology, people started to interconnect sensors in grids, start to interconnect these sensor networks to lighting networks inside the buildings or in the cities, and we create somehow independently, almost at the same time, the connected lighting concept. And this is the situation that we are today. From one side, we try to have the human-centric lighting, and from the other side, we try to improve the connected lighting. What will happen from the next years, and say in the next 5 to 10 years? The first thing is to make interacting human-centric lighting systems with connected lighting systems, and this interaction has to take into account also the human being. We cannot make abstraction of ourselves in the system, and if we do that, we can arrive that will be maybe the graal for lighting technology would be the smart lighting. The smart lighting, I don't like the term smart because in a technological system, nothing is smart. In a technological system interacting with human being, the human being is smart, and you know very well that is not always the case. Well, but let's use that term. And if we develop those smart lighting, and just look around you, the number of lamps that you have inside your room, outside in your city, and you discover that you have a excellent mesh of things that you can use as basis in order to install sensors. Sensors, they are doing different things, not only actions for lighting. And you can understand that way that lighting itself, due to the fact that it is everywhere, is present everywhere, can be a very solid basis in order to develop smart building concepts or smart cities. And of course, behind you have smart electrical grids and all that stuff. And what you can do more, then once you are in this smart configuration, you make things interacting between them. This is the Internet of Things, and you have something that is going well beyond that we do today. You have a lighting system that is able to communicate with the end user, but also able to understand what are the needs of the end user and provide the right quality of light, the right quantity of light, but also you can use light in order to communicate with smartphones, with laptops, what you can imagine. And in that case, the light becomes a service. You go well beyond the economical model of our industries, which is today selling you lighting system and lamps. Maybe in the next 10 to 20 years, it will be much more interesting to give you as a gift a lighting system and ask you to pay for the light that you use as you pay for the gasoline for your car. And maybe the system also can collect the data, and the provider of light can sell your data to someone else. The light becomes a service and your data becomes a product. This is a completely different way of thinking at the economical level. And of course, then we can, all of us, start saying, okay, I want to use a smart lighting system that recognizes me when I arrive nearby my home and open my door, switch on the light, makes my coffee if I want to drink coffee right in back. But I don't want that my lighting system send a message to someone else telling that be careful, George, or I don't know what is your name, is arriving at home, and if you're doing something that is not very well seen, most probably you have to refrain. Well, where start the technology service? When stop the technology service, and where start our privacy? This is a very important problem that we have to solve for the next years. But in any case, today we are going to that direction. Look, for example, this is an example in street lighting, smart street lighting in Toulouse. What we do here, we use cameras embedded in the lighting poles. Here in France, no question to make facial recognition, which is doing in some other countries. But the system, the camera can recognize a human being, a bicycle, a car, a cat. And if the system recognizes a cat, no need to switch on the light. If recognize a human being walking, we need just to switch on one lamp nearby the person, one lamp behind him, one lamp in the front of him, and that's enough. If we see a car going with a given speed in a going direction, then we can switch on several lighting poles and then switch off when the car passes. And this offers the right quality of light, the right quantity of light, and of course save energy, because for the large part of the night, the light is switched off. And now imagine all that with the lighting poles communicating, but communicating also with smart cars, that they can communicate between them with the lighting poles. And then the lighting poles, they can communicate with system inside our buildings, but they can communicate also with your smartphone. And if you take the small humoristic drawing here, if you are drunk, your telephone can identify that you are going back and forward, and of course can try to wake you up, but also can broadcast to the smart cars that be careful, someone which is drunk can arrive suddenly in the road, and you can hit them. Well, you see what we can imagine. And be careful, this is not scientific fiction. We have all the necessary tools and technologies in order to do things like that. And that gets us to the ultimate solution for lighting system. That is the frontier that we expect to have maybe in the next 1 or 2 decades, is the right human-centric lighting. What means right? This is the most important word. First of all, I want to say that illuminate something or someone doesn't mean to flood objects, people, buildings with light. If you do that, we'll obtain exactly the opposite effect that you are looking for. But what we need to do is to take the technology, our technologic knowledge, evaluate the impacts. I will show you some rapidly afterwards, and combine that with our needs and our social needs. And then use all this global system in order to light up when we need it, where we need it, and light up to a smart way. This is the most interesting way to use the word smart here. What are the impacts? The impacts, as I told you, is not only impacting the energy, but our impact is in the environment. And I show you just one, the billion of tons of CO2 released every year in our atmosphere. And I spoke also about mercury. But if you take any technological impact, from the moment that you create it, you are using raw materials, from the moment that the system is dead, and then you can recycle it or not, you can recover some materials. That means if we want really to understand what is the impact of any new technology, including any smart system, we needed to go through not only with indicators like the carbon footprint, as we do today, but we needed to execute a full life cycle assessment that is done using ISO standards. Just an example, if you do that, and you take two different countries, you take France. France, we produce more than 70% of our electricity by nuclear power. And of course, nuclear power doesn't release CO2. We have other wastes, but let's forget them. And from the other side, you take Indonesia. Indonesia, 87% of their electricity is generated by oil and coal. Well, now if you take very efficient lamps, LED lamps, and you look what happened, what is the impact of the global impact of those lamps in France or Indonesia, you will discover that in France, the most impacting phase of that product is its production. The manufacturing of LED lamps is the more impacting to our environment. That means if we like to reduce that, we need LED lamps with as long as possible lifetime in order to reduce the number of lamps that we produce. If you go to Indonesia, in Indonesia, the most impacting phase of the life of the product is the energy used during its lifespan. In that case, that you need here is not probably LED lamps of very high quality with very high lifespans, but you need lamps with which are as efficient as possible. You see, this type of life cycle assessment can help governments to design what type of products they need to introduce to their markets. Okay, I go fast here. Something else that we need to take also into account, and life cycle assessment doesn't take into account that, is the pollution of skies due to artificial lighting and with all the impacts to our fauna and flora. And we know that we are not in the right path if we still continue to light up our cities and our buildings without taking care of our ecosystem. And of course, we need to take care of ourselves because our health, our well-being is depending on the light and the variation of light. Because the daylight is varying during the duration of the day from something like very strong quantity of light and very cold quantity of light. The sky is blue or gray when it's raining. That means we have high color temperature and uniform light in that case. And when the sun is going down, we have low color temperature, non-uniform distribution of light, and lower quantity of light. Our internal clocks are just synchronized with this variation of light, and this ignite in our organism the production of different type of hormones like melatonin or cortisol that at a first glance they will control our cycle of wake up and sleep. That means now if you use artificial light, more and more artificial light, yes, I finished, this is my last slide. What will happen? If you don't use the right light, you may disturb your biological clock, and this may have a huge impact on your health that can go up to a situation that cancers may become more and more probable for each one of us. Well, that was my my last slide. Okay, I will show you that one. If we need really to create a innovative light system, we have to take into account a huge number of parameters. We need to execute high quality of scientific research.
Hello, sir.
Hello.
Pleasant day to you, ladies and gentlemen. Today we've got another awesome speaker for you, and it's quite an honor for me to introduce. He's going to speak about power electronics for grid integration. Professor Frede Blaabjerg was with ABB Skandia Randers, Denmark from 1987 to 1988. From 1988 to 1992, he got the PhD degree in electrical engineering at Aalborg University in 1995. He became an assistant professor in 1992, an associate professor in 1996, and a full professor of power electronics and drives in 1998. From 2017, he became a volume investigator. He is honoris causa at Université, Politehnica, Timișoara, Romania, and Tallinn Technical University in Estonia. His current research interests include power electronics and its applications, such as in wind turbines, PV systems, reliability, harmonics, and adjustable speed drives. He has published more than 600 journal papers in the fields of power electronics and its applications. An editor of 10 books in power electronics and its applications. He has received 32 IEEE Prize Paper Awards, the IEEE Pearls Distinguished Service Award in 2009, the EPE Council Award in 2010, the IEEE William E. Newell Power Electronics Award in 2014, the Willem Ken Rasmussen Research Award 2014, the Global Energy Prize in 2019, and the 2020 IEEE Edison Medal. He was the editor-in-chief of the IEEE Transactions on Power Electronics from 2006 to 2012. He has been distinguished lecturer for the IEEE Power from 2005 to 2007, and for the IEEE Industry Applications Society from 2010 to 2011, as well as 2017 to 2018. In 2019 to 2020, he served as president of IEEE Power Electronics Society. He is vice president of the Danish Academy of Technical Sciences too. He was nominated in 2014 to 2019 by Thomson Reuters to be between the most 250 cited researchers in engineering in the world. The energy paradigms in many countries, e.g. Germany and Denmark, have experienced a significant change from fossil-based resources to clean renewables, e.g. wind turbines and photovoltaics, in the past few decades. The scenario of highly penetrated renewables is going to be further enhanced. Denmark expects to be 100% fossil-free by 2020. Consequently, it is required that the production, distribution, and use of energy should be as technologically efficient as possible, and incentives to save energy at the end user should also be strengthened. In order to realize the transition smoothly and effectively, energy conversion systems currently based on power electronics technology will again play an essential role in this energy paradigm shift. Using highly efficient power electronics in power generation, power transmission, stroke distribution, and end user application, together with advanced control solutions, can pave the way for renewable energies. In light of this, some of the most emerging renewable energies, e.g. wind energy and photovoltaics, which by means of power electronics are changing character as a major part in the electricity generation, are explored in this paper. Issues like technology development, implementation, power converter technologies, control of the systems, and synchronization are addressed. Special focuses are paid on the future trends in power electronics for those systems, like how to lower the cost of energy and to develop emerging power devices and better reliability too. Once again, ladies and gentlemen, help me welcome Professor Frede Blaabjerg to the platform. Welcome, sir.
Thank you very much, Colin. Can you hear me clear? I just want a confirmation I'm not speaking in nothing.
Yes, sir, we can hear you clearly, sir.
Oh, that's fantastic. Also, thank you for the invitation to come and do this presentation virtually. Unfortunately, we could not meet physically this year, but we have some hope in the future that this again will be possible. However, this afternoon, I will share with you some of my thoughts in terms of power electronics technology and the future vision in this area where we are applying it for renewable energy systems. Let's see. Yeah, let's see. Yeah, okay. So what I'll do this afternoon is I will first give an overview about the power electronics and the development in renewable energy systems, and talk about how it's evolving, and the demands are, of course, making the direction for the development of the energy systems. As we know, renewables need power converters between the generation unit and the grid, so I will discuss them too. Finally, I will touch the basic control of such kind of systems, including some of the challenges we are seeing now, and then finally a summary, and I hope to have some discussion with you also afterwards. But just before we go on board in the technical matters, let me just introduce where I am just sitting now. We have India here, and it's around 8 hours flight, 9 hours flight to Copenhagen. This is a large photo, so I'm located up here, and typically we fly to Copenhagen from, for example, Delhi, and my city is called Aalborg, and Aalborg is located 400 kilometers in this direction from Copenhagen, or direct flight to Aalborg. It's only 30 minutes flight. And Aalborg University is close to 50 years today and has 22,000 students and more than 2,000 faculties. And if we should characterize shortly a little bit about Aalborg University, that is the teaching model we are applying for our students, meaning that all our students, they work in teams when they do studying on the different programs. Half of the time in this team working spirit, they work with a project which is formulated as a problem, and then the team of students, they should try to solve it. The other half time they spent on getting courses in order to do the projects. So this is what is called the PBL Aalborg model as a problem-based learning model. And this is becoming more and more recognized around the world, that this is a very strong way to do engineering education. If we should say something about what you maybe knew about Denmark, otherwise I think many people, they know about the Danish poet Hans Christian Andersen, who has done a lot of fairy tales. The university has a strong engineering program, and we have in the last years been ranked very high by US News, for example, especially in engineering. And we have been ranked number 4 globally, number 1 in Europe. And one of the main reasons is that our research has a very, very strong international impact. And here you can see some photos. If you have a chance to come to Aalborg, we are located a little bit from a city center typically, and this is where we are, but we also have campus downtown where we have a waterfront also, but you can also see some other nice photos about how it looks like. And as I was saying, we have this engineering program where, an example how they are studying at our campus, all of them, they get a room where they can do their project work, and they have a certain time to do their project, and that means they have to work close together. And for the moment, we have been sending them home because of the COVID-19, but now they are back again and work close together in order to do their studies. Typically, there are 4 to 6 students in a group. And one out of the 18 departments in Aalborg University is the Department of Energy Technology. And as you can see, the name says, it is technology we have in focus, but also energy. So it's not a classical electrical engineering department, because we are both looking at power generation, including electricity, but also thermal heat to heat the houses. This is especially relevant in the northern part of Europe. But then we look at power transmission, distribution, and efficient use of electricity, as well as efficient use of heating and technology related to that. In the last, let's say, 2 decades, we have also been working with other alternative generation systems like wind turbines, fuel cells, photovoltaics, storage systems. And some of those topics are on the agenda here for this presentation. And the way we organize ourselves is, and this is also illustrating how we have a cross-disciplinary department, because we have in our department 6 sections which cover where all staff is belonging to. And then we have what we call multidisciplinary research programs, where the staff is then taking active part in doing some research. So we have 3 classical areas, I would say, in electrical engineering. They are electrical power system, power electronic systems, electrical machines. And then we have some other areas which make it more cross-disciplinary, and that is fluid power and mechatronic systems, fluid mechanics and combustion, and thermal energy systems. So you can see this is really cross-disciplinary also with mechanical engineering things. And so then we have defined a large number of research programs where we try to have coordinated activities. And here is a list of them, a little bit ranked according to how much power electronics is involved. So that includes efficient and reliable power electronics, wind turbines, photovoltaics, automotive, and then a lot of other activities also. And the department has more than 110 PhD students, as well as 50 faculty members. So in total, we say we are around 300 people. And we are quite well, let's say, equipped. In general, this is the area of energy technology, where this part here is our staff and student building, and this part here are our lab facilities in different aspects in terms of energy technology. So we have a lot of space, and because we have such kind of as a high-level lab facilities, we can also say that it's attractive to come and visit us for 6 months, 12 months, and all the time we have between 60 and 80 guests working together with us. But we have facilities like medium voltage, high voltage labs, a lot of power electronics lab, and also large scale facilities. So you're always welcome to come here. And just in the last years, we are also now at the university building a new university hospital. Okay, that was just something about where I'm coming from. Let me just go on board for the power electronics technology and the renewables. And if we look at the energy system, this is a diagram I showed to you before. We can see that in a system with where we are dealing with electricity, in a lot of aspects we are applying the power electronics technology for doing an efficient power conversions. And you can see different applications here where some of them are extremely mature, others are more in the emerging area. Some of the mature are for sure drives, LEDs, appliances, automation, and so on. And some of the fast-moving things are now and not so mature, for example, electrolyzers, maybe also interfacing a large-scale batteries to the grid system. And we also know the renewable generation needs power electronics, so this is also applied a lot. So we can say that power electronics is really in all kinds of aspects in terms of energy system. And last but not least, which is what is emerging fast for the moment, this is the electrical cars, because there you need many kilowatts of power electronics in order to deal with it, as well as chargers. So if we look at the power electronics history, this has been more than 100 years as this electrical power conversion, where we try to have an efficiency as close as possible to 100%. So we differentiate typically between before 57 and after 57, because in 57 the Vice-Rector was invented, and that made a very big difference in terms of electrical power conversion. Before that, mercury arc rectifier, vacuum tube rectifier was there, and we could do power processing. They were not so reliable, but by the introduction of the Vice-Rector silicon-based, a large number of circuits was possible to do, and this was really in the 57 and onwards a fantastic time in terms of new circuit topologies and so on. But then later on, of course, there was power diodes. In the 70s, the power bipolar transistor came. Also, in addition, the power MOSFET came, where the gate was a capacitor we were looking into. And the next big step was the invention of the IGBT, which is combining the benefits of power bipolar transistor and the MOSFET. And in the beginning, this was not a very robust device, but now it's really a robust device. And then we can say a new era is coming now, came already in the around 2000, as the base material for devices was shifting from silicon to wide bandgap devices. And in the early 2000s, the silicon carbide diode came. And if we look at what is going on now in terms of device technology, we see many wide bandgap devices which are extremely interesting to apply with fantastic performance parameters when we integrate them into equipment. So we can say we have a phase 1 and a phase 2, where phase 2 is the modern power electronics, which has now been there for plus 60 years, where the switches has constantly improved, the losses decreased. We have been able to reduce the volume, and that means increased power density. Cost has gone down, and controllability has also been better and better for the devices. If we then look at the technology itself, as the power electronics technology, before the Vice-Rector, this was where we applied in specific applications, radars and medicine and others. But after the Vice-Rector came into play, as a circuit topologies were invented one by one, we also needed better modeling methods, so our control could be robust and do what we like to do. As the switching frequency was increasing, because the switching losses was going down and the conduction losses were going down, then we could do faster and faster dynamic control. And also in that context, the digital systems have become more and more into the systems. And then I would say today we do not see a lot of new power circuit topologies. Now it is more the application which are driving the innovation and the technology, and where we have in mind, and we have focus on thermal management, EMI, reliability, modularization, and so on, and including also the digitalization of the power conversion. So this is a road where, of course, when you recall the diagram I showed before, which is not stopping, this is just increasing more and more, as we see a lot of ambitions in terms of making the transportation electrified and the generation carbon neutral. So let me just give you some trends in terms of renewables. This one is the installed renewable capacity from 2000 to 2019. And the capacity has been increasing from 800 gigawatt to 2,600 gigawatt. So this is really an amazing development. The blue one here is the hydropower, which have been there for a long time, while the emerging technologies like solar and wind has taken the most growth combined with bioenergy. So this has been an amazing development. And if we look at what is the annual market in terms of a renewable energy system, this is illustrated here, saying that the annual market in 2018-19 has been around 175 gigawatt, and it has started at 20 or 15 gigawatts. So this is an amazing growth. Then you can ask, is that a lot compared with the overall installation of generation? And I have to say, yes, it is. You can see here the share between non-renewable and renewable generation, where today more than 70% of all renewable all new electrical installations are renewable, while only 28% is non-renewable. So this is an amazing distribution. And if we look ahead, this is going to be more towards renewable generation. If we take my country, which have ambitious goals in terms of renewables, and the dominating generation system is wind, because our wind conditions are strong. And so we have a lot of wind all the time. you'll remark that if you come to Denmark and live sometime. And what you can see here is the amount of energy produced from 2070 to what we expect in 2027. And you can see it seems to be around 70% of all electricity will be covered by wind. But what also this one here will show is that it's a combination of putting the turbines onshore and offshore, and the highest growth we expect to see offshore. In general, we can say energy systems have to become changed, and I think Denmark is a nice case of what is going to happen, because what is going to happen is that we are moving from a centralized production to a decentralized production of electricity. And here you can see the Danish power system in with red dots, which indicate the generator units. They are large, based on fossil fuel, and the black one here are the transmission system. And then we have been through a transition in terms of power system to 2015. So this is 30 years of history, where you can see we have got a lot of dots, which are distributed generation. We also have dots in the ocean. And in that way, we today have thousands of generating units to supply the Danish system. What you maybe also can see is that we have done some strong connections to our neighbor countries. This is up to Norway, where we have a DC link, as well as to Sweden, where we have a DC link. And that means the energy system is undergoing a significant transition, where the past was based on units like this, large synchronous generators, but few, because they are the red dots, to a lot of dots, and then the interface are power electronic based. And we have to be able to cope with that in terms of the technology here, as well as how to control the whole power system in a safe and reliable way. And that involves significant advances in how we do integration to the grid, at both transmission, distribution, and also at the control level. In Denmark, is the renewables really dominating in terms of the electricity? And I have here a few numbers. You can see here the renewable share in 2070 was 71% of the whole electricity consumption, and in 27 it expected to be 90%, and in 2035 it's expected to be 100%. So and in that context, the wind is really dominating, but there are also other sources like wood, a little bit solar, and way little straw and biogas. But that's going to raise, because we have a very strong agriculture system. So we are a little bit the front runners in terms of implementing renewable technology. If we take the wind power and the progress of that, this is illustrated here for 20 years of record. You can see it has not been so big in the beginning, but in total 2019, the installed capacity was more than 600 gigawatt, and the market in 2019 was 60 gigawatt, and the size was around 2 megawatt. So this is an amazing development, but a linear increase. It's not in terms of accumulated power. It's not an exponential function anymore. It was in the beginning. And if we look at the technology, this is amazing to follow from 90 to 2025. So this is around 45 years, where we have been developing the technology from 50 kilowatts to 500 kilowatt 10 years later, to 2 megawatt 10 years later, to look into technology where we maybe have we will have 14 megawatt of wind turbines with blades diameters of more than 220 meters. So this is a fantastic engineering achievement to be able to do that, not only electrical engineering, but also seen from a mechanical engineering perspective. And the color here indicate how much power electronics is dealing with the overall power of the wind turbine. And from the beginning, the turbines was just a troublemaker. Later, it became a self-organizer, but today it's both an active contributor and a stabilizer. Here you can see the top 5 wind turbine manufacturers by installations and their technology. You have Vestas, Siemens Gamesa, Goldwind, General Electric, Envision, and you can see the power range here. Also, who has the big turbines. But what is also interesting to remark here are the concepts applied in order to do the conversion. And you can see double-fed induction generator, permanent magnet synchronous generator, squirrel cage induction generator, and even also the synchronous generator by DC is a technology applied. So we can say no system fits all wind turbines. So this is interesting, but also nice seen from electrical engineering perspective that there are many interesting things to be working with. The photovoltaic is another area where a rapid progress have been, and maybe even more rapid in terms of capacity development. This diagram here is from Enlotek, who every year records in terms of efficiency of the cells. And you can see that every year we see new records, and the record is close to 50% by some technology, and some others have way low efficiency. And in between, this is what we are using today. But in general, you can see that the efficiency is going up. And then if we are able to combine that with long lifetime and low cost of production, then it becomes more and more attractive to do PV installations. And this is what we see in terms of market trends, that in 2018 we have installed 500 gigawatt, and in 2019 it's also it's 100 gigawatt more. So in 2019 600 gigawatt was installed, and this has almost an exponential character because the price of the PV has really been lowered a lot in the last years which have been there. And here you can see who are the main manufacturers, and looking at the names as well as where are the headquarters. China is a very leading country in terms of being able to manufacture the photovoltaic technology, but there are also other countries represented on this top 10 PV manufacturers. And if you look here, this is just to say that in 2019 it was 97 gigawatt of installed power. If we know that the photovoltaic system, they need inverters in order to extract the maximum power delivered from the sun. So we also need we need inverters. And here from 2019 you can see who are the main players in terms of inverters. And in this case, Huawei, Sungrow are the two dominant, as well as SMA. And then there are many other players on this market, which in 2019 was close to 100 gigawatt. So this is a lot of power electronics which have to be manufactured and shipped and installed around the world. So what is driving the technology is the demands for them. And if we look at the wind turbines, in respect to the electrical power conversion, we can say we have to the left here the generators. They need control of speed, so that means variable speed, variable frequency, variable voltage. And we have at the other side the grid connection, where we have constant frequency, constant voltage. And then in between, when we do the power conversion, we need to balance the interface in terms of storage, so we are not having too much pulsations at both sides. We also need high reliability, because if that's not high, we lose power production. As well, high power density, because the power conversion stages are normally placed on the top of the wind turbines. So there is a heavy demand for strong cooling, reliable conversion. And what is important to look at when we do a design of such kind of converters are their loading conditions. This is also what here is named as emission profile. And the main loading is naturally the wind condition, which is illustrated here to the right for 1 year. But what can also influence is the temperature, because the temperature is fatiguing the material, as well as can be critical for some parts of it. So this is important to have in mind. And the wind can also be turbulent, and we need to deal with that in our control system. So what has driving the technology for the last 20 years and have forced power electronics to be used, especially into the wind turbines, have been that as the role of the wind power becomes more dominant in the grid, then the system operators, they want to have the same functionality of the wind turbines like they have for the conventional power plants, like controlling reactive and active power, but also other features, synchronizing power, damp oscillation, short circuit capability, as well as emulating something like the inertia which is present in the big synchronous generators. And that means grid codes are have been announced and followed, and they are constantly on a development and dictating the demands for the power electronics and the control system we are working with. And here are some examples of that, where the specifications are how much power you generate as a function of the frequency. So that means you have to take active part of the frequency control as the primary control of the power system. And specifications here says that you have to reduce the power production if the frequency becomes too high. So this is one specification where you have to be able to do that as a turbine manufacturer. There can also be another characteristic like this, dependent on how the basic principle is of the whole power system. And then we have here to the right what I would call a PQ characteristic of the wind turbine, indicating that, of course, we have all the time to deliver the power which is available, but at the same time to be able to deliver both capacitive and inductive reactive power to the grid in order to control the voltage at the PCC. But what has challenged the technology has been the requirements during grid faults. And to the left here, you have some waveform curves showing where you need to stay connected to the grid system. And there are demands today that you have to stay connected 150 milliseconds to the grid at 0 voltage. And this can be a challenge, and you have also to stay connected for one second. Where the voltage have been lower than 30% for that time. So those dips can challenge the technology. But at the same time, there have been added demands that when the voltage drops, then we have to provide reactive power into the grid in order to see if we can keep the voltage staying there. And also at 0 voltage, we have to be able to inject reactive current. So this can be a tough demand. So if we look at the other side for the photovoltaic system, yes, there we have at one side the PV generator, and we have at the other side the grid. So the PV generator is DC, so it's not the same like the wind turbine generator, but a lot of other features are the same. But so the DC, we have to ensure that we get the maximum power out of the panel, totally independent on the conditions the panel are seeing. And then at the AC, we need to deliver frequency and voltage, which both are constant. And then the demands for the power electronics we look at here is, of course, high efficiency, high reliability. And in terms of high reliability, thermal management, temperature management can be important. And many photovoltaic systems are put outside, so just below the panel, so they can see more influence from the surroundings. And the photovoltaics, they can be located at many levels at the electrical system. So especially at low voltage, if we are not careful and some faults happens, then they can do island operation. So we need some kind of island protection of the inverters in order because of safety. And here is illustrated what we again can call the loading profile. To the right is the irradiation, for example, from Denmark. So how much kilowatt hour per square meter. And to the left is the temperature such an inverter will see over a year. So you can see the temperature can go up up and down a lot. And and for the irradiation, this during one day, this can be a nice waveform. It can also be a very variable waveform because clouds and so on can influence the energy which is available. And if we look at the specification for such kind of systems, they can be a little bit different because the power level can be different from several kilowatt to up to hundreds of megawatt. And as we go up in size, then the specifications are alike the wind turbine systems, while at low power, more specifications are put on the power quality we have when we are applying those PV systems. So power quality and islanding detections are important. If we look a little bit at what has been a challenge for the technology, as what are some of the key factors in terms of PV and how to achieve a low energy cost. Some roadmaps have been specified in order to achieve that, and this one is indicating what we looked at in 15, where are we today. So what is important to lower the cost is the degradation rate of the panels, because if that's too high, then the production of power is low after certain years. So there have been tough specifications to achieve that. But also the inverter lifetime has seen heavier demands going from 15 years in 2015 to 30 years in 2020. So that means people like us who works in the power electronics area, we have to look at better design, so we are ensuring that we do not have to replace the inverter. Otherwise, we have to take that into account in the calculation of the PV energy cost. Let us look at the converters we are applying as the power electronics. And if we look at PV, we can say we have a wide range of power level, from module converters to string inverters to central inverters, where for the module, this is typically 300, 400 watts as a DC-DC conversion, DC-AC. For the string system, we have DC-DC and then DC-AC. And for the central inverters, we will typically just have DC to AC. And the voltage level we have in the DC link is 450, 750, and 1500 volts. So you can see this is going up as the power is going up in level. And the connection to the grid is single phase to three phase, dependent on the power level. And the discussions for the topologies are: do we need to have galvanic isolation or not to the grid system? And if we have, if we have galvanic isolation, we can do this low frequency or high frequency. If we are applying high frequency, then we can shrink the size. And we see this mostly because size matters and material matters. But many countries, they want the highest efficiency for the installation. So avoiding the high frequency, the transformer is very interesting. So having a PV, DC-DC, DC-AC, and the challenge in this case will then be that we have direct connection between the grid and the panels. So that means if we have switching here, then we will also have that the potential of the PV panel will jump up and down, and there can be a risk that we have a leakage current flowing through the large volume of the panels. Here are some examples I have taken with this presentation here, how we can realize this. Here are two examples of where we have what we call a module integrated inverter, where you have a panel, then you do some internal boosting of the voltage, then you do DC to AC conversion. And there are, of course, different ways of doing this. But in general, we can say when we look at a PV system, it's an interplay between, do we need to boost the voltage here in order to do maximum power point tracking? How fast do we need to switch this combined with the filtering we need to have in order to ensure that the power quality is good enough. And then cost and efficiency are the main drivers in terms of selection of the technology. If we go into the string inverters, there are different solutions. There are what we call, for example, here a single-phase system where we have a full bridge for DC-AC conversion. We have PV strings here, and then in between we have a kind of separation of the DC part by a switch. And this can be done with what we call an H5 transformer-less inverter, or we can have two devices and then apply a split capacitor here, and this gives very good ground connection. And this is what we call an H6 transformer-less inverter. But when we talk about inverters for the moment, which are the most popular, there's no doubt that the neutral point clamp converter is very popular because we have very good control of the ground current, and at the same time we have a strong quality of the output voltage here, so the requirements for the LC filter is not very big. For the central inverters, the fundamental idea is that we have a number of, we have PV arrays here with DC-DC converter, and then a central inverter going DC-AC, and then we have a low voltage to medium voltage transformer where we then collect all things into a high voltage transformer. So we are connecting to the, to the transmission system. And one of the things going on is that we want to have higher voltage at the PV panels, because this can lower the copper losses in the cables, and we can also save other components in the system layout. And this is illustrated here, where you have an open circuit voltage of a PV system of 1.5 kilovolt. And then we do a DC to AC conversion. It looks natural to do this, but that also means that we will have from ground to the panel here, we will have 1.5 kilovolt in voltage difference. And there can be a risk that we will see a degradation of some parts if we are not carefully in terms of design. But there are many arguments for going into this direction, and we already see now in those years here solutions which are able to, as a centralized inverters, which are operating with this high DC voltage. If we move into the turbine configurations, there are fundamentally two, where we have the double-fed induction generator system. The grid is connected directly to the stator, and we are dealing with the AC and DC conversion by two converters. So we do AC to DC and DC to AC. And the beautiful thing with this topology here is that we only need to deal with the slip power of this generator, and the power level of this AC to DC and DC to AC converter is only 1/3 of the total power of the turbine. But at the same time, we can keep full control of the active and reactive power. In the challenge in these systems are two, but it is applied, it is solved. But the challenge is that if we have voltage dips here, then we will also see this directly at the stator, and we need to cope with that. And another thing is the maintenance, because we have directly connection to the rotor side, which is a rotating part. The alternative is naturally what we call a full-scale conversion system. We have a induction generator or synchronous generator to this side. Then we have a full-scale AC to DC, and then we do DC to AC. And we need to deal with the full power 2 times. And that is costly. It's a 100% converter. But it has a clear advantage that we can decouple the generator operation with the grid operation. So if something goes wrong, one of the other sides, then we can almost separate how we want to deal with that. So we see this in more and more application because it has benefits. The converters we are applying are different. For the lower power, relatively lower power, we typically apply voltage below 690 volts, and this can be two-level converters like you can see here. I'm sure you know them, and have a DC link. In case the generator is a synchronous generator or permanent magnet generator, instead of having an active end to the generator, we can just have a rectifier end and then boost the voltage so we can connect to the grid system like shown here. And this is also applied in some technologies. If we want to scale up in power, for example, for the two-level voltage source converter, we can do units of 2 megawatts and put them in parallel. In that we can do more high volume production, as well as we can achieve a good, a better reliability, because if one fails, then we can still operate. The reliability, high reliability, can also be achieved by multi-winding generator, like illustrated here, where you have 9 phases, and then 3 phases deals with one converter, 3 phases deal with another, and 3 phases deal with the third one. As we go up in power and voltage, the obvious solution is to move into a multi-level converter, and a 3-level converter is being seen now. But the implication is then also that the generator voltage will exceed 690, so we are moving into medium voltage, as well as the DC link will be high, 3 kilovolt or something like that. So the layout of the power circuit configuration needs to be medium voltage oriented, and that is a little bit more complicated in practice. We are putting the wind turbines into the ocean to form farms. And here is one example of a 400 megawatt, and we will see this more and more. And if we need to transmit the power to shore, we can do this either by high voltage AC, like illustrated here with 2 different configurations, and then a collector transformer, which is going to the AC, and then we have an AC cable. If the distance is too high, we need to move into DC, and the natural way is, of course, to have an AC grid, medium voltage AC grid, for example, 60 kV, and then transmit up to high voltage, and then do AC to DC conversion at a high level. But looking at the topology, it's a natural thing to think in that direction, that we have a medium voltage DC grid, and then we don't need this DC to AC conversion, and then step up the voltage from medium voltage to high voltage and then do the transmission. We have not seen so much yet there, but I'm sure this will come in the near future. What is also going on when we want to make such multiple wind turbines to operate together to be a power plant is that we are introducing energy storage to do more power smoothing, and the energy storage can be located in the DC link of the turbine, or it can be located centralized in order to operate and improve the operation of this wind power plant. And we see this more and more in both locations. What is interesting, especially, for example, is if we have a centralized storage system, this can also help to do black start of the AC grid. In that context, but also in order to improve the performance of wind power plants, we see reactive power compensators to be put into the grid connection system in order to compensate for reactive power, either at, for example, the medium voltage or at the high voltage by using STATCOMs and SVCs. Okay, time is running. Let me stroll you through how to control the renewable energy systems. And here is shown a control structure of a PV system. And we can say fundamentally we have a 3-layer control structure. And to the left here, you have the PV panel. To the right, you have the grid. In between, we have a DC-DC converter, we have a DC link, and then we have a DC-AC system. Remark here is a DC chopper, and this is especially to deal with a situation that the grid voltage disappears suddenly, and we need to cope with the energy coming from the generator side. But we have typically 3 control loops. One is a very fast control loop where we do current and voltage control, as well as grid synchronization. Then we do the next level is what we call PV system specific control, where we do maximum power point tracking, also anti-island protection and power limitation. And then we have more advanced features which are coming more and more into such kind of systems. Grid support, applying energy storage, do protection, increase the power quality, panel monitoring, fault right through, and so on, and many aspects to study. One of them, which is very important and has been known for decades, is the maximum power point tracking, because the control look into a black box, and where we try to extract maximum power. And as illustrated here, what is varying is the irradiation. This can be the temperature, and thereby the maximum power point tracking will change, as well as there can happen degradation of the panels. And today we are really able to do this very nice. Here you have two situations where we can see the available power and then what we can extract of power, and you can see they are totally aligned with each other. So this is possible for a 3 kilowatt system. But what is moving into this kind of systems is that we want to have more and more controllability of those systems. So if this waveform here is the available power, then the system operator can say that, no, we want not the maximum power all the time, but we want to have the possibility to decrease the power production at a certain rate, and the PV plant should be able to do that. We also want the PV plant to have all the time the possibility to put more power into the grid if needed. So this is what we call delta power operation. And then we also want cases where there is a maximum power which we are producing, despite that there are more power available from the sun and the panel. So this is really moving into that direction, that the demands become higher. And so constant power operation is one of the features, and I have just taken with me here that it is possible, and it is possible, for example, to move out of the maximum power point operation and stay out there without putting anything in, which is dissipating the power. So we are not utilizing the panel in the maximum way. So this is shown here. Here's the available power, and here's the actual output power at two different locations. If you look at the control of the wind turbine system, I can share with you that the basic, the organization of that is the same like for the PV. So we can utilize controllers, philosophies, and so on. Of course, we are dealing with larger power in many cases, but here you have the generator, you have the grid in between AC to DC and DC to AC, as well as a braking chopper. So we have very fast loop to do the synchronization and control, but both at the generator side and at the voltage side, at the grid side. And then we do maximum power point tracking. We need to be able to do grid support, fault right through. And the next level of control are other features like having high power quality, do protection, black start, and also introduce energy storage in the operation to have a better power quality sent out to the grid, as well as emulate some of the same features like synchronous generators. The big discussion now is how should we operate such a wind turbine system as well as a wind power plant. The typical way we have done it so far has been that we have put a reference for power and reactive power, and then feed power into the grid at the point where we are connected. So this has really been the dominant way to do that, and that means when we do this kind of grid feeding operation, the grid is controlled other places, and so the frequency and the voltage is given by the conventional synchronous generators. But if more and more synchronous generators, they are disappearing, then we need also...
Hello, sir.
Yeah?
Sir, we have to conclude here because 5 minutes left.
Yes, I'm with. Okay. I'm very soon.
Yes.
And the way to do this is to form the converter to operate in a grid forming way. So we do the frequency and we do the voltage. So this is another way of doing it. and it is a more complicated one because we do not control the power directly, and that can violate a little bit how we are controlling the generator side. So these are some of the challenges, also the mix we need to do. So let me end my
MTT Society and IEEE conferences since 1990, including the MTT President, Vice President and Secretary, Chair of the IEEE Conferences Committee, Founding Chair of the Radio and Wireless Symposium, and Chair of the International Microwave Conferences. He has contributed a column on microwave business to IEEE Microwave Magazine since 2011. Just to share the brief of what he is going to be sharing on us, a little abstract. Regeneration came into use over 100 years ago, but is not commonly used today. The challenges of maintaining stability and the need for quenching circuitry have limited this application. A new approach using multiple resonators overcomes these limitations. This talk will show how a multi-resonator regenerative circuit acts as a single pole with stable Qs of up to 7,000 and without the need for quenching circuitry. A wide range of applications are possible, and some of these will be discussed in this session. Mr. Schindler, welcome to the platform.
Thank you, Mr. Chairman. Thank you for your kind introduction. As you already heard, my talk is on innovative generation without quenching and its applications. And why does not want to advance? Okay, there we go. So here's the agenda for today's talk. I'll go over the background of regeneration, a bit of its history. We'll go over some of the limitations that we see in that conventional approach to regeneration. Then we'll get into a novel multi-resonator regeneration approach and its properties, and show you some demonstrations of that technology and what it can do. Finally, going into some applications and talk a little bit about the company Anlotek. Okay, so we'll start by going over the background. So regeneration is a simple concept. It's also known as positive feedback. So what you see in this diagram here is an amplifier, so there's some gain. Some of the output signal is fed back to the input as positive feedback. And what you will see, there's a delay line in the feedback loop. What you will see then is an infinite series of poles based on the length of that delay line. So this is not necessarily a useful concept, but if one adds a resonator then into the loop, then we get a single peak, a single dominant pole, where the loop delay determines the period provided the resonator is roughly the correct frequency. The initial use of this concept about 100 years ago was in the tube era, and tubes at radio frequencies at that time suffered from low gain, so regeneration was required. Super regeneration was a concept that added quenching circuitry because regeneration tends to go unstable. Oscillations are one of the primary issues with regeneration, so quenching circuits became important. But eventually it fell out of common use because of the problems with stability and control limitations, and the fact that gain was more easily available to achieve with other approaches. So the tuned regenerative circuit and super regeneration can be attributed to Edwin Armstrong, shown here on the left. Among other things, he was on the faculty of Columbia University in New York. He's an interesting character. He is credited for inventing super regeneration, the super heterodyne circuit, commonly used in almost every receiver, and frequency modulated transmission as well, FM radio. He was involved in patent disputes on all of those topics, and in the end, in frustration, he committed suicide over the frequency modulation patent. But here he's shown in happier days on the right side, with his wife on their honeymoon, where he brought along his first portable radio based on super regeneration. Okay, so let's take a look at this tuned regenerative circuit using a single resonator. So this is the same circuit we were looking at before. We couple some of the output signal through the delay line and the resonator back into the summer. And what we have here is both variable capacitance, so we can vary the resonant frequency, and we have variable gain, which allows us to vary the amount of feedback that we have. Looking at the S-plane, you can see that we can change the gain and move in this axis, and we can change the resonator and move in this axis. The result is, as we change the gain, the amplitude, we can increase and decrease Q. So if the nominal Q here in green for the resonator is then affected by increasing the gain and higher Q, or decreasing actually negative feedback reduces the Q. And then by tuning the resonator with the variable capacitor, you can up and down in frequency. So let's take a look at what that means. So here is a Nyquist locus for a resonant loop, and what you can see is if we move the amplitude in the loop, the gain in essence, we can move closer and further away from that potential instability. And if we vary the capacitance, we can move closer and away from the stability in addition to changing its frequency. So, and this is one of the primary issues with regeneration. So there are multiple intersections, and so noise even will cause potential stability. So the goal is to be able to be as close as possible to the intersection to get as high a Q as possible. But since there are multiple possibilities for intersection, instabilities can happen that weren't predicted, and that's a challenge. So let's take a look at a solution that we've come up with using multiple resonators. And this is multiple resonators in the loop, but it still, in the end, acts as a single dominant pole. So here is our concept. So it's the same kind of controlled loop. We have now three tunable resonators and gain throughout the loop, and then we have adjustable phase, adjustable amplitude. The three resonators can be anywhere in the loop. We show them here in the forward path. They can be feedback path. The gain can likewise be anywhere. We've distributed it around the loop in multiple locations, but it all could be in the feedback path, or it could all be in the feed forward path. So let's take a look at why this concept is so well behaved, and it is. Why we've chosen three resonators, why there is phase control, and what trade-offs are. Okay, so let's take a look at what an ideal single resonance looks like. So here we have our operating point, similar to before, and as we increase the amplitude, we get closer and closer to the stability. And you can think about the distance between these vectors as being related to Q. So you can see as we get closer and closer and closer, the distance gets tighter and tighter and tighter until you hit the intersection and you get the point. Now, something to keep in mind as you tune, we'll get some skewing. So the closest intersection now is not aligned with a little bit offset. So what does that mean? So as you can see here, as we get closer and closer to the intersection, we actually have the two intersections that causes the potential instability. Now, if we take a look at this curve here, right? So here we've tuned, and we have 2 points here. So here we have, once again, 2 intersections, so instabilities will occur. So this is the highest Q that can be achieved without running into control limitation. So looking now at different numbers of resonators, so the green line here is that same circle that we saw in the previous 2 charts. So this is just a single resonator, right? And so as we're tuning along this dashed line, right, as we get further and as we tune further and further and further, we get potential instabilities. But this shows now what happens when we have 3 resonators in the red line and 5 resonators in the magenta line. So what we really see is diminished returns once you get past 3 resonators. So 3 resonators seems to be a pretty nice place to be. 2 resonators, which is obviously between the 2, is also quite effective. And it really depends on how far you want to be able to tune. So you can see here, we can tune 3 resonators quite far away. All right, so let's talk about control of VHL3. So one of the interesting things is that you can self-calibrate. So all you need to do is reduce the attenuation around the loop or increase the gain around the loop until the onset of oscillation. Measure that frequency. Note the Vice-Rector setting that were used, and now you know the peak amplitude of that circuit. So as you back off Q, you know what the pole location is. So there's no need to pre-calibrate, no need for a factory calibration. You can do this in the field, you can do it periodically. So this is possible because it's well behaved, and there's well-defined instability, and there's no hysteresis. So let's take a look at this circuit in detail and a demonstrator that we built. So once again, here is this. Here's the circuit. We have a combiner, 3 tunable resonators, amplifiers throughout the loop. Our variable gain is in the feedback path, and we also have some phase control. This is, of course, phase control just to make sure that we get into the right region for input, right? So we need to have positive feedback around the loop. So we need to make sure that we can forcefully tune ourselves into that range. So what we actually have here, 90 degrees. And here you actually see the circuit. So we were able to do this on a conventional circuit board. The resonators can be seen here circled in red. There are 3 coupled line resonators. There's a reactor in each. The forward loop is here. You can probably make out the amplifiers along the way. And here's the feedback path. This is the phase shifter. The additional gain. So this was implemented at 1.8 gigahertz using off-the-shelf components, and we've been able to demonstrate well over 7,000 that were stable. This concept can work at virtually any frequency. It really depends on the availability of various components that are needed. We built this on a circuit board. It can easily be done on a semiconductor as well, especially as you go higher and higher. So these are the measurements we made on the circuit. So this is just a factor of increasing the gain around the loop or decreasing the attenuation of the loop. This goes up to a Q of 7,000. The resonators themselves, the passive resonators that were used, have a Q of 74. And then you can see as we increase the feedback, Q is increased to 7,000. So we're getting Q multiplication of about 100. And if we go a little bit further around the loop, then we achieve oscillation as well. This is a broadband response, just to show that circuit was well behaved over a wide frequency range. And you know, this is just it's not really an issue with this concept, but it depends on the layout of the circuit board and things like that. That's quite a bit of gain. Avoid other potential feedback within. So you don't get spurious oscillations of passband. So here we have a single, very high Q pole that functions very, very well. And so a high Q pole, obviously, this just shows the frequency tuning. Now I have to, you'll note on the left-hand side that we have a considerable gain slope as we tune across the frequency band. There's also a measurement glitch. We actually had an unterminated port our devices that created that's not inherent in the device, measurement error. But you can see this significant gain slope. This actually had to do with the coupled line resonators. Circuit board technology does not necessarily give you the highest precision in terms of what we want, especially the relatively basic circuit board processing needed metallic substrate. So the gaps were a little bit larger than we had designed, which resulted in an undercoupled resonator. So it was a bit higher than expected, and it had a bit higher loss than we expected as well, especially the lower end of the band. But still, we had enough gain around the loop to get the high Qs and as well getting possible. So here you see it tuning across the band. And here you can see we can correct that now. Flat tuning. Okay, so this is takes a little time to absorb. These are two plots of the exact same data. Looking at the right hand plot first, so this axis here is when we control the gain around the loop. So this is basically the C from the circuit, and this is the frequency. So we're essentially measuring on a network analyzer here. We are not tuning the frequency, we are measuring the frequency. And so we start here with very little gain around the loop, and the gain around the loop is direction. So what you can see is first of all, that the amplitude range of change here until we achieve oscillation. So Q is increasing as we go this way, and if you were able to make a slice through here, you'd see that the Q peak decreases as we go down to this range until we get to here, where we're down to the nominal Q of 74. On the left hand, we have the exact same data plotted as a contour plot instead. So now you can see, and the red line is just the peak when we're in this region, and it's actually the oscillation frequency. So this just shows you as we go from low gain around the loop all the way up to high gain and oscillation, that the frequency is quite stable. And you can also see with the contours that the contours get closer and closer and closer, so to vary in this region here. All right, so let's just take a look at what we designed here. So we have a 3-resonator circuit. It provides this stable, controllable high Q pulse. This is a natural circuit for integration on a semiconductor. We are basically enhancing resonators. So Qs only need to be around 10, and we can enhance them by 10, 100, etc. So here we have an approach that allows us to use transistors, gain elements, to replace bulky reactive elements, which makes it natural for semiconductor integration. Obviously, the size of any component on a semiconductor chip is at a premium, since that drives cost. So here we can use gain, which is small and easy to provide on a semiconductor. We use that to replace a reactive element, which is by its own nature large. you can make it smaller with a lower Q, and we can do that. Make a low Q resonator and increase its Q. We've shown that there's a straightforward self-calibration, a nice digital control. The ATL3 can operate over a very wide frequency range, and pretty much any frequency where a host semiconductor has usable gain, you can make this circuit work. And in fact, as you go higher in frequency, the passive resonators become smaller and smaller, which makes it quite attractive. So this circuit now can be a building block for filters and lots of other applications. So let's take a look at a 3-pole filter that we demonstrated using these 3 resonator circuits. So here's our 3 resonator circuits. We essentially use 3 of them. So the nice thing here is we have 3 independent poles, and they can be used to design any filter. So there's 3 poles of adjustable Q, frequency, etc. So you can make a maximum flat filter, you can make a equal ripple filter, you can design for steep skirts, whatever your desire is, you can cascade as many of these as you like to make whatever filter characteristics you need. So here's an example of just taking 3 of them, and we've got a filter design with relatively sharp skirts and some ripple. Here we have 4 and maybe not 5 high Q poles. And what you can see kind of in the background of each of these slopes is the characteristics of each of the poles in the design. So for example, when you get to the 5-pole filter, so here's a very high Q pole. The ones that factor into the band center are much lower Q. The ones at the band edge, the skirts are much higher. All right, and so here's our demonstration. So this is the same circuit board I showed you before. We just have 3 of them in cascade. We have a control interface with a Raspberry Pi, and you can control this from the computer. And here's some characteristics where we're able to tune the frequency and the bandwidth and the frequency. And I'll show you some data. So here's our 3-pole filter. We adjusted it for very tight bandwidth. So here's 0.2% bandwidth at 1760 megahertz. So very tight filter characteristics. And here we are adjusting the bandwidth. So we went from 3 megahertz to 4 megahertz to 10 megahertz. And with 3 poles, you could keep on going wider. Once again, ripple or maximum flat, whatever characteristics you use. Tuning it over frequency, so it's the same 3-pole characteristic. Now we've tuned it over relatively large band, and we've demonstrated over 20% range very easily. This is a characteristic of this specific circuit board. There certainly are ways to make a much larger tuning range in design for that. So let's take a look beyond these initial demonstrations. So we demonstrated tuning bandwidth of 20%. So wideband resonator design could also be used. So just think about the design of wideband VCOs. They can often cover an octave. So same approaches are applicable here. Keep in mind this is a building block, this ATL3 circuit that we've reviewed. It's a high Q tunable resonator. It can be used to design any filter with any desired passband, and those passbands are adjustable. The MP3 demonstration that was just reviewed has confirmed. So this could be used in all kinds of circuit applications, very wide range, and I'll show you some examples. Something that we've done in the lab was to demonstrate we can enhance and tune other resonators. So we have our loop. If we put something else in that loop that has a dominant pole, we can now adjust it. So we did that with a SAW resonator, and SAW resonators have inherently the IQ. We were able to enhance that SAW resonator that had made it to about 300, I believe, to a Q of over 18,000, very stable. And we're able to do that as well. Obviously, when you're dealing with high Qs like that, the tuning range is going to be smaller, but certainly demonstrates the ability to fine-tune and control IQ. Okay, so let's look at some of the requirements and the limitations we have. So this ATL circuit is natural for on-chip integration, as we've already discussed. Gain is something that's easy to get on a semiconductor. IQ is difficult to obtain. So here we are compensating for low Q with gain, which really parallels a lot of that what we've seen being done in the semiconductor over the years, where transistors are used to replace other approaches. Transistors are it's cheap and easy to make semiconductor. Low frequencies are a challenge for on-chip implementations because of resonator size. So you know, the circuit we've demonstrated here at 1.8 gigahertz, that certainly could be done on chip with low Q resonators, but it would be a relatively large chip. If you go to 10, 20, 30, 50 gigahertz, the resonator size is very, very small. And in those cases, board level implementations are actually a challenge. So some really require high frequency, required to be on chip, and low frequencies might try to use board level implementation. So the circuits I showed you up to now use varactors as variable capacitance element, and that's certainly viable at pretty much any frequency. Switch capacitors can also be used, be very, very attractive. Switch capacitors are quite commonly used in a variety of circuits today. If you look at the smartphone that you carry in your pocket, it has switched capacitor networks, both in some of the transceiver components for VCOs, since the varactors don't have an adequate tuning range, and you'll also find switch capacitor networks at the front end as tuners to adjust the antenna to the front end of the smartphone. So certainly switch capacitors are an attractive option as well, and you know which approach you take depends on the process capabilities, and indeed you might actually use a combination of switch capacitors for rough tuning and varactors for fine tuning, which is a common approach in fencing. Okay, so let's take a look at an application example. And so we're going to look at a super Nyquist DDS. So what do we mean by that? So direct digital synthesis, or DDS, basically uses a digital to analog converter to synthesize a signal. So digital control is used to periodically generate an amplitude. Those amplitudes are output through that control to provide a signal. Just think about you know, a step function based on the clock of that D to A converter, and you can approximate a signal. So it'll be a step like function. If properly filtered, you get a sinusoid, simple tone, etc. You can actually modulate that signal just by appropriately adjusting the digital input to the DAC. The frequency you can generate is limited to half the clock frequency, just the Nyquist limit. But a very attractive way to generate signals at a variety of frequencies, basically limited by how fast you can have a clock on that. If you look at the spectrum here, so the clock frequency is this. So this is frequency, you know, spectrum. So here's the clock frequency. and here's the fundamental output. So it's much less than the half. And there's a variety of spurs that you see, this step-left function instead of a smooth sine. But the interesting thing is, so you have this clock frequency. We actually see images of this fundamental around the clock and around the harmonics of the clock. Okay, so this is called the first Nyquist zone. This is called the second, the third, and the fourth. So what we can do now is we can actually, through proper filtering, pick out one of these images, and now we can make very pure signals at much higher frequencies in the clock. And the interesting thing is this signal will move exactly as this one does as we change it and modulate. So they're perfect copies of the signal of the fundamental. So we've got this high Q filter, so obviously an attractive way to do it. So what we do is we have our normal DDS, so a DAC with some digital inputs going to it, clock generation, etc. And we've got our filter. We control them together. And so the spectrum that you see coming out of the DDS with all its various images and harmonics and other spurs is nicely cleaned up, and we just pick out the image that we want, and fundamental is suppressed. It's a very nice high frequency. And so we have indeed done that. So we've taken that filter that we've already shown you. We've tuned it for a 10 megahertz bandwidth. So about 5% bandwidth, centered at 1875 megahertz. Very similar to what we saw before, nice clean filter shape. And we used it with a direct digital synthesizer. So we used an analog devices, AD9914 DDS, and it has the option to use an internal clock or an external clock. In this case here, we are using its internal clock. So the AD9914 is limited to an output frequency of about 1.4 gigahertz. And so in this case here, we've got a fundamental input and output rather, and a bunch of other spurs. And here, after we go to our filter, when we give you a closer look at what we're actually seeing here. So we have a clock at 2400 megahertz. So you can see the clock spur right here. We have set it up for a 528 megahertz output, the fundamental output shown here. And then the first image is now at 2400 minus 528, which gives us 1872. So this is the first shown right here. And then we go through our filter. The fundamental actually can't be seen anymore, or even the noise. So very effectively. There are some spurs here. These are all broadcast signals, so we didn't have a screen room. So we picked up some broadcast signals. This is the image we're trying to pick out. So you see that very nicely. And then we have a bunch of additional images. Plus, actually, we get a harmonic of this. So you see a very nice cleaned up spectrum. Okay, so here's another demonstration. Now we used an external clock at 1100 megahertz and 326 megahertz output. And in this case, we're looking at the third image, get us 1674 megahertz output. So here you see our very cluttered spectrum and the result afterwards. So now let's take a look at the details of that. So here's the fundamental output at 326. Here's the clock at 1100 megahertz. And here are a variety of images and a bunch of things. So we go through our filter. Once again, the fundamental is completely suppressed. You can't see it. Very little noise. We have a bunch of broadcast signals into our measurement. And then we see a bunch of images. And here's the image we've selected, and the others are pressed by 50 dB or more. They're a very effective way to generate a very high frequency signal. So when you're generating signals, phase noise is obviously always a major concern. So here we show phase noise measurements. Now here we're using a 24 megahertz external clock, not the clock that's external to the 9914. We use a very low phase noise clock to ensure that possible. So now we've set it up for a 475 megahertz output, and at the first image is 2400 minus 528 or 1925. So these are all measurements at 1925. So we start by looking at this orange line, if you will. So this is the phase noise that we see coming directly out of the 89914. Now, when I say out of the 89914, this is not the phase noise at the fundamental. This is the phase noise just at the image itself. The phase noise at the fundamental, as you would expect, is better just because the amplitude is higher, a higher signal level at the at the fundamental output, and the same amount of noise, so relative phase is better. And that's just inherent, and a common trade-off you see as you go to higher and higher. But what you can see here is in the remaining curves, we've adjusted the Q from 280 back to 280 all the way up to 940, and we see no significant change. And this is very much as expected. If you take a look at the ATL3 circuit that we have, it's fundamentally a bunch of gain elements. Gain elements typically are not significant factors in phase noise. Oscillators are where you see sources of phase noise. And some people have speculated, well, we're operating these IQ circuits. Are they really more like locked oscillators, or are they really, or aren't they? And we got a well-controlled Q. The circuit is stable. We're nowhere near oscillation. 1000, and this verifies that all we're seeing. The reactors can obviously also be a source of phase noise. In this case, not a measurable factor, but we could certainly consider the lower phase noise requirements where the reactors might come into play. And in that case, we put the password, but instead have a significant impact on phase. So the other thing that you can do with a PDS is you can have it generate a modulated signal. And the 89914 that we used to generate a chirp. So we used it to generate a chirp. The filter is still the same as I showed you a few charts ago, which is to say it had a bandwidth of about 10 megahertz. And we just adjusted the chirp for different frequency ranges. So here we have an 8 megahertz chirp, so it fits well within the passband of the filter, so flat output. Here we have a 25 megahertz chirp, so it extends well beyond the 10 megahertz bandwidth, so you start characteristics. And here we have a 50 megahertz chirp, so a wideband chirp, and all chirp is much broader than the passband itself. You'll notice that there's an offset to 2 dB offset and 4 dB offset later. This was purely done mathematically, just to help in visualization. If I hadn't done that, these lines would be on top of each other and challenging to see what's going on. Okay, so let's take a look at some of the potential of what we've shown you so far. So we've shown you this ATL3 circuit, so this 3 resonator circuit, and then a 3-pole filter based on that circuit. So what we have is a novel approach to generating high Q, very well in semiconductor technologies. There's some interesting characteristics to these circuits. They have gain. Now, as you have positive feedback, obviously, as you're approaching oscillation, gain gets higher and higher and higher, and so that needs to be taken into account. So this really drives you to reimagine the systems architectures to best make use of high Q poles. So, for example, in a receiver application, well, the filter is going to be generating a lot of gain, so you don't need other elements. So you really want to just integrate the filter poles into the architecture of the system. You want to take advantage of that gain rather than creating a lot of gain. Way, this is not a plug-in replacement for conventional filter. So re-architecting will give you the best results. And then looking at integration, however many resonators you want to put in your pole. So APL circuit is a key building block. It's the resonator core. We built ours with off-the-shelf components. And there's a limitation when you use off-the-shelf components. Many of you have designed semiconductors, that's what I mean. So the amplifiers that we purchased, they come with some basic characterizations or S parameters. We know what their noise figure capability is. We know what power limitations are, but that's all we know. If we design in a semiconductor instead, so if we use a semiconductor process design kit or PDK, be silicon or gallium arsenide, these provide comprehensive models for the components, primarily transistors, but everything else that the process can yield. So now we actually have not only knowledge of what the small signal performance of the transistor is, we also know what its noise performance is and how the noise by the matches, it's the feedback, so you can really design and optimize the performance once you get into it. We haven't actually built an on-chip version of the ATL, but we have done some designs and for the potentials to optimize it, and that really is the logical next step for optimizing the performance. So let's start to wrap up here. We see endless potential applications. Test and measurement is kind of a great starting point when you're making test equipment or test systems. Filtering is often a requirement. Isolate what you're trying to measure from everything else. So high Q filtering is often a key aspect of measurement. But the other interesting thing that you need in test and measurement is stimulus. So you need to generate signals. And as we've shown you with the super Nyquist concept, a very attractive way to generate very high frequencies that are indeed tunable. So the DDS can not only modulate, it can easily move its frequency up and down. And we have a filter now that can track it. Not only that, we showed you how we can get different images. We can continually move from image to image. So we could use the first Nyquist zone to go up to less than half the clock frequency. Then you can change the clock. You can go to a different image and continue from there. Then switch to the next image. So you can get a very, very broad band sweep with a DDS going much higher than the clock frequency. great for that kind of an application. Obviously, anywhere you need to generate a signal. Attractive application, anywhere you need a filter. So as I mentioned, the performance has been demonstrated, but we haven't optimized it. Semiconductor integration is the next natural step. And how exactly you optimize that circuit depends on the applications and its requirements. So you can imagine that filtering on the receive side of transfer is very different than on the transmit side. I'm going to talk a little bit about our company. We're a small company. We have a talented technical team, and what we're doing right now is partners and demonstrating our technology with them. What our goal is to develop partnerships, leverage our technology property. So we're based in the United Kingdom, actually. I'm in the United States. Have a small set of people around the world working on this technology. We have a portfolio of IP related to Q enhancement and some adjacent IP as well. We've had some nice demonstrations. I shared this in a number of different forums, and we're working on a number of different applications. And just one last thing to share with you are some references, both a couple papers that we've published over the last couple of years that go into the demonstrations that I've reviewed with you today. The third reference is an application note from Analog Devices, which really does a very nice job of not only describing PDS, direct digital synthesis, but also the Nyquist zones and recent images. And then the bottom two are some of the original references on regeneration and super